All right. No homework due today because we didn't do any new stuff last week, but we'll get back on that schedule next time around. All right. So I would like to talk some more about the quotient topology today. And I want to talk about some fun new types of shapes you can get by making quotients. So the quotient topology using, I want to talk about the quotient topology using equivalence classes of points. This is something that equivalence classes. This is something that I mentioned briefly whenever our last real class was, but we didn't really talk very much about it, and I want to talk a little bit more about this point of view on the quotient topology. All right, so the idea, remember, is if you have X is a topological space with some equivalence relation, which our book writes with a little tilde. So you have a topological space, but you also consider some of the points to be equivalent with one another. And the quotient topology is what you get when you just actually combine those equivalent points into single points. Each equivalence class of points becomes a single point. So this is some equivalence relation here, and our book writes X star as the set of equivalence classes. All right. And X star becomes a new topological space using the quotient topology. So the quotient topology makes X star into a topological space. All right. And the standard example that you should have in mind when it comes to this is, I would say, like what I imagine is the interval becoming a circle. So this is a quotient. You can think of this like a function which wraps the line around the circle, or you can think of it like an equivalence relation where we consider all of these points to be just themselves, but we consider the two endpoints here to be the same point over here. This is the point of view of equivalence relations. So here, the equivalence relation, or the equivalence classes, I'm not going to try and write the relation as a relation. Really, all that matters is the equivalence classes are each point that's not on the end just stays by itself. The only ones which actually get glued together are the two on the end. So if this is the interval 0 to 1, let's say, just for convenience, then the equivalence classes are just, X by itself for X in the middle. And there's one special class which consists of 0 and 1 together. Those are the equivalence classes. And then the quotient is what you get when you make everything in those classes into individual points. Now these ones already are individual points, but this had 2 points and they get combined into the same point. All right. If you think carefully about this, this is more or less the same thing that happens when you do a quotient in group theory, quotient by a normal subgroup. It amounts to making equivalence. Oh, me too. A quotient in group theory is when you consider things to be equivalent when they're in the same cosets, and then you sort of consider each coset as if it was its own group element in the quotient group. It's the same thing, although it's not important to understand that if you don't understand quotient groups or whatever, but it is the same idea, which is why we use the word quotient for it. All right, that's the standard sort of easiest example when you identify the two endpoints of the interval and you get a circle. All right. Another way to describe these classes in the book, they call these classes make what the book calls a partition of the original space X. That is, we are just dividing the original points into some categories. And they are, in this example, all of these individual points on the inside, they are all in their own category, and then the two on the ends are in the same partition, the same category of points. And the quotient just glues together all the stuff with everybody else in their own little set. All right. Let's look at, so I just wanted to look at some more interesting examples. I actually brought some weird things, a little show and tell here for one of the examples at least. So one thing that we've already seen before is we can do here's some familiar quotients. A cylinder from 0, 1 cross 0, 1. So if you start with 0, 1 cross 0, 1, it looks like a rectangle, right, with all this stuff on the inside. This is 0, 1 cross 0, 1. But we can create a cylinder by gluing together the two, let's say glue together the two vertical edges on the two sides. When you glue those together, you kind of have to wrap the thing around, and what you get is the cylinder like this, right? This is obtained by gluing together the two vertical sides. So how would I express that in terms of equivalence classes or a partition? I would say, I mean, it's like the previous example, but I would say every point on the inside just stays by itself. They don't get glued to anything. And also, actually, the points along the upper line and the lower line, also they do not get glued to anything else. But the ones along the left side are glued to the corresponding point along the right side. All right, so can we write those down? So the classes in this case, they look like, first of all, the points that just don't get glued to anything would be just themselves. I'm writing it as a point in two coordinates because it's in that rectangle over there. This is when x is not on the end, so x is not 0 or not 1, so I'll just write 0 less than x less than 1. And the y coordinate actually can be anything including 0 and 1, right? I'm talking about every point in here, even the ones along the top line or the bottom line, just not on the two sides horizontally. So, like so, right? These are all the points sort of on the inside or across the top and the bottom. They stay by themselves. They do not get glued together with any other points. So that's one type of classes. The way that they write this in the book, actually, sorry to squeeze this in. They write those, they just give them names. So let's call those the A's. Those are the individual points which do not get glued to anything else. Those are all of that type. And then there's also sets that involve gluing the left side to the right side. So this would be, I will say also B, I'm going to say BY. And these look like 2 points, 0, y and 1, y. Again, y can be in this range. So this says that for every vertical y value, you have 0, y, which would be 0 x coordinate at this height, and then also the same y coordinate but at 1 x coordinate. And those are considered to be in the same equivalence class because I'm going to glue those points together when I do the quotient. All right. So my classes look like the individual points, that's the ones on the inside, and then I have classes of 2 points each that get glued together, the ones on the left side and the right side. This is really exactly the same as this, where you had individual points and then also a class of 2 separate points. It's just you have to do it for all different y coordinates. All right, and what you get is the cylinder. So this is a description of the cylinder as a quotient of the square. Any thoughts about that? Now we also talked about if you additionally glue together the top to the bottom, so actually this whole diagram here, we often sort of represent it by just drawing maybe something like that, where the two arrows indicate those two sides. I'm going to glue them together in a way which sort of matches up the two arrows. All right, so this is a cylinder. I got a few more interesting examples of things you can do with this same strategy of start with a rectangle and then glue it together in increasingly weird ways to get different shapes. So another way that we have seen before is if you do like this. I glue the sides together, and then I also glue the top and the bottom with each other. So this, when you glue the sides together, if I were to write this sort of in two steps, first of all, gluing the two sides together gives me this kind of a shape, where I still have not glued together the top and the bottom. But now if I continue and glue together the top and the bottom, what does it look like? We've seen this before. Yeah? Some Julia? It's a torus, yeah. If you take this cylinder and imagine you kind of, stretch it out a little to give yourself some room, and then you bend the two sides together so that those two circles can join up. This is, as an intermediate step, you could draw it sort of like this, right? Where I intend to glue this and that. I think I put the arrow the wrong direction. It should be like that, right? So that the two arrows are, when they meet, the two arrows should be pointing the same direction. Eventually, this becomes a donut type shape, which I only know how to draw like that. Where this right here is where those two arrows got glued together. All right? Sorry, these should be the double arrows now. They got glued together. So this is a torus. What do the classes look like here? The equivalence classes. Well, it's similar to before. We have a bunch of points which are just going to stay by themselves. They're not being glued to anything. Those are the points on the inside of the rectangle. So I'll write those as A, X, Y, like we did before. These are just XY by itself. These are the points which do not get glued together with anything else. And that happens when X and Y are both on the inside, not on the edges, right? So if X is between 0 and 1 and Y is between 0 and 1, not including zeros and ones, that point just stays by itself. What about the ones along the bottom edge? They are glued to the ones along the top edge, and the ones on the left are glued to the ones on the right. So to get the left and right, actually I'm going to write the same thing that I did last time. For every point 0, comma, y, this is considered to be the same as the same point 1, comma, y. So this means if you have a point on the left side, x coordinate 0, that point is meant to be the same as the same point but on the right side, x equals 1. All right, and it would be true for all y's. And then we're also going to glue the points along the bottom to the points along the top. These are points which have any x coordinate, but the y could be 0 or 1, and they would be considered to be the same. So I'll call this maybe cx. This is x, comma 0. That's a point along the bottom. It's meant to be the same as the same point along the top, which is x, comma 1. And we do this for all the points where the x is between 0 and 1. All right, those are the three types of equivalence classes here. There's the points on the inside, which don't get glued anywhere, the points along the sides, and the points along the bottom. Yeah?
I just have a question, because in the last one you included for like B of Y, you included Y like as 0 and 1.
Really?
So
Oh,
why is it not?
I did. I think it doesn't matter. In this case, so the question is, this would involve, say, I'm gluing this point to that point. Now, do you even want to do it on the corner? do you actually want to glue this point to that point on the corner? And the answer is yeah, you still do. Actually, I think it does matter. You got to put it in here because otherwise I didn't describe anything about the corner. So this says all the corners, the two corners on the bottom should be glued together, and also the two corners on the top should be glued together. Yeah, thank you for that. It's technicality. It should be there though. If I left those out, then the corners actually wouldn't fall in any of these three categories. But you have to describe every point as being part of one of those categories. Thanks. All right, so this we've all seen before. I would like to talk about three sort of more interesting examples that we have not seen before. So one is a variation on the cylinder. Start like this, but I'm going to do it like that. So I'm putting the arrows in opposite directions. So this means you are going to glue the two sides together, but one of them you gotta sort of flip over before you glue it to the other one. All right? So this means you kind of, if I'm gonna glue the two sides together, maybe I'll imagine it being sort of stretch the thing out a little to give yourself a little more room to work with. And when you can imagine if you had a big strip of paper like this, bring these two sides together, but turn this one over so that the two arrows actually match up when they hit each other. Anybody ever seen that before? Done this? This is something, I don't know. I used to play around with this kind of thing when I was a kid. This is when you do this in real life. Sort of, it looks vaguely like a cylinder. I'm going to try and draw this carefully because I'm not a great artist here. It looks vaguely like a cylinder, but it has a twist in it. The thing gets twisted over like this. And then can you tell what I'm trying to draw there? It's like a cylinder, but you twisted it over. You can easily make this shape in real life out of like a ribbon or something. If you just tie the ribbon onto itself, you can get like a normal looking sort of hoop. But if you twist it once before you tie it, then you get this shape. Anybody seen this before? This has a name. Do you know the name of it? This is called the Mobius strip, or the Mobius band sometimes. The Mobius strip. And it has many interesting properties to it. Maybe I should have brought some ribbon that we could all play around with. It has interesting properties involving the sides of this shape. If you think about an ordinary cylinder like this shape here, it has sort of an outside and an inside. Like if you had one of these in real life, you could paint the outside, blue, and you could paint the inside red if you could reach in there. All right. This shape, though, is not like that. If you say, starting here, let's say I'm going to paint the outside blue, right? You have to visualize in your mind. You paint around the back side of this, right? Paint. Come by around here, you paint this thing blue. But when you go through the twist, actually, you're going to end up back over here, but on the other side and still painting it blue, all right? The fact is, this shape does not have two sides. It's kind of the inside and the outside, or the front and the back of it, are actually, they're connected. You can get from one to the other by just walking around the shape, all right? Strange but true fact. So this is sort of a one-sided shape. Another interesting thing about this in terms of the two sides, you could imagine if you had one of these in real life and you had something like a coin on it with a heads and a tails side. I'll try and draw the picture again. It's like this, right? If you start with your coin, say here, and it's on the heads side, I'm imagining this is sort of like on the front facing me. If you send this around the thing again, it'll go all the way around, come back to this point, but it'll be on the inside, and actually you'll be looking at the tails side here, all right? This is kind of a strange thing. Like, this cannot happen on the surface of a sphere, for instance. If you have a coin with the head side up and you just move it around, it's always going to have the head side up. But on this, on the Mobius strip, actually, if you start like this and you move it around this way, it will end up in the same place, but now it'll be upside down. The tail side will be up. All right. This is also weird. It's a one-sided shape where you can do that weird thing about I think the conclusion here is, like, really on this shape, there is no such thing as up or down, because if you have something that you think is facing up, you can move it around the shape and then it will be facing down, but in the same location. So here, a head coin can, I'll just say, slide around. You're not actually like picking it up and flipping it over. All you're doing is sliding it around the shape. Can slide around and become a tail coin, right? Very strange. There's a word for this in topology. This is called, so the terminology is the Mobius strip is non-orientable. That means there kind of is no such thing as up or down on this thing. A more technical way you can say this is there is no such thing as a unit length vector field on this shape. Unlike the sphere, you can make a unit vector field that always points outwards. But you can't on the Mobius strip, because if you try to follow your outward pointing arrows around the shape, they end up being inward pointing, and then your vectors will be inconsistent. Yeah.
Wait, I don't understand how it could become the tail side. Is that just because the head's pointing out on the inside, so
Yeah, right.
so it doesn't actually flip over, like it's not.
I'm not
Like
sure
if
what
it
you
was
mean.
like a clear, we would see the tail on the outside, but it would still be like the tail was up against the surface of it. The coin doesn't actually.
Yeah, so in this case, I'm imagining that this thing has sort of no thickness,
Okay.
right? And the coin is floating on it,
Okay.
and it goes
Okay.
around. As it goes around, it gets flipped, not because you picked it off and flipped it, but because the shape itself has like a flip in it already. Yep. Strange. All right. So this is another example. This is actually an important topological example, and it's a weird thing to think about in this way. But you only realize how weird it is when you look at it in this way. Actually, if you just look at it like this, it doesn't really seem all that weird at all. It's just a square where you have identified the two sides in a somewhat weird way. Can we say, actually, what are the equivalence classes here? So to get this thing, technically speaking, what are the specific equivalence classes that we need to use to make that gluing happen? Well, again, all the points on the inside just stay like they are. So I'll give them names like we have been. We have just individual points stay by themselves if they are on the inside. So I'm going to say x between 0 and 1, and the y can be anything. It could also equal 0 and 1. And then the other set is the one in which things are glued together. So I'll call this y's, because I'm going to say, you have to be a little cute about this, but can anybody say what point does 0, y get glued together with? In the example of the circle, I glued 0y with 1, y. That would be, here is 0, y. Down here is 1, y, same y coordinate, right? The same height. Now, you don't actually want to glue it to that point over there. Actually, in this example, I want to glue it to this point up here, right? It's sort of in the same spot, but on the top rather than on the bottom. Can we say, how would you write that? I'm trying to write this in coordinates. First of all, what's the x coordinate? It is 1, yeah. It's on the right-hand side, so this is a 1. What about the y-coordinate? That's the more interesting thing. The original y-coordinate was here. I called it y. Can anybody say what's the y-coordinate of that point? Remember, in the y-axis, this is 0. This is 1 up here. You got an idea?
1 minus 1?
Yeah, it's 1 minus y. This is not so obvious, but if that coordinate is y, that means this little distance here is y, and the point I'm looking for is up here at the same distance. So the point which is distance y from the top is actually 1 minus y. Yeah, excellent. So this is the appropriate equivalence relation to use to get the Mobius strip. And this is for all y values like that. All right. It's actually from a certain point of view, very simple way to describe what the Mobius strip is. Certainly this description of the Mobius strip is much easier than trying to write it down like in coordinates in R3. The ordinary cylinder you can write in cylindrical coordinates if you want to. That's very simple. But the Mobius band in R3 is not easy at all to write in coordinates in R3 in the traditional way. But as a quotient of the rectangle, it's very simple to make sense of. All right. There's a lot of fun things you can do with the Mobius strip. I was encouraged to do this when I was a kid by my math teachers at some point or something. You can get weird things can happen if you take one of these things and you decide to cut it like horizontally around the middle. Anybody know what happens? What do you end up with? 2 things? 2 separate things? Yeah, actually I don't recall. I think you get one big thing with two twists in it instead of 1 twist. It's something weird happens when you do this. Play around with it. Get together with your 3rd grader little brother or sister and see if you can make some of these in real life and you can play weird things with it. Actually, you can tell it's much easier to imagine doing that if you just think about it on this picture. And let's say what I'm talking about is cut it in half like that. What do you end up getting? Actually, you get sort of the strip across the bottom here will connect in sort of like this, but then this side actually will end up here, but upside down, and then this side will end up back down here. So I think you will get, it's just one big thing. It just goes sort of twice as long around, and it will have 2 twists in it because every time you cross this line, this boundary line, you get a new twist. Strange. You can play around with it. It'll be fun. I saw once a bracelet that was shaped like a Mobius strip, and it had I don't know where I saw this. It had the Lord's Prayer, the Our Father, written on the bracelet in the shape of a Mobius strip, and I thought that was like topologically interesting to me, but it had sort of a good practical reason because the Lord's Prayer is kind of long to write on a bracelet, but if you write it on a Mobius strip, you can actually write it all the way around, like both sides. You get 2 sides rather than making it so that you write around the outside and then you have to flip it over to see the second half of the prayer. It's not like that. It sort of flips itself over as you go. And when you get to the end, like the last word is right next to the first word, but it's upside down. I thought that was interesting, topologically speaking. I don't know if there's any deep theological meaning to that, but I thought it was interesting looking. All right, I got 2 more weird shapes that you can do similarly. So here's a weirder one. How about, I'm gonna glue, so can I just refresh our memory? This one, if you glue the sides and the top like this is the torus, all right? What if I do that, but twist one of the gluings? So let's twist the top and the bottom. So I am going to glue these two sides sort of straight, but the top and the bottom will be glued backwards or with a twist. All right. What is that? So this is something. Topologically speaking, it's not all that weird if you don't try to think too hard about what it is. You can think of, if you're like a little guy who lives in this thing, if you walk off the right-hand side, you come back the left-hand side, like Pac-Man. If you walk up the top, you come back up the bottom, but kind of on the other side, or flipped over, all right? Pac-Man doesn't typically do that, but you could easily make Pac-Man do that. Like it doesn't like violate the laws of physics or something like that. And it's just a somewhat weird, topologically weird thing, but it's not all that weird in my opinion. Can we try to imagine what this looks like if you actually try to like make this out of paper or rubber or something to bend it around? You need it to be rubbery. So the first step would be, first of all, let's glue the two vertical sides together. That is easy enough. That would become a cylinder where, those two sides became just one thing. But the weird thing is now I have to glue the top to the bottom, but with a twist. All right? And when I was doing this before, when we got the torus, I wanted to kind of stretch it out a little, right? So if I were to stretch it out a little, like this, I'm trying to draw the same kind of a thing. But those two circles, like on the end here, these two caps, you don't just bring them straight together. You gotta turn one of them around so that they meet in the opposite direction. So it's like this and this. Maybe see how to do that? You've got to turn one of them around so that they meet in the opposite direction. The idea would be something like, if I leave one on the bottom, say, and I'm going to turn this one over. Let's say this one is like that. And then this one has to come down like this. In that, sorry, it's hard to see what I'm drawing here. Make it a little bigger. This way, so that those two things can meet in the same orientation, these two arrows. All right. Now, if you really want to do this in real life, if you think about make this looks kind of like a tuba or something. If this was actually made of metal, you would not be able to connect this to there, because you have to. This part would have to like go through that part of the tuba, right? So this analogy here of trying to think of this as an object in R3, actually it doesn't really work for this shape. What you end up with is something which looks like it has a part that goes sort of up like this. Oops, sorry. This is not going to be a great drawing. And then this part comes down, somehow like drills through that, and then ends up connecting to the bottom of it, like that, all right? This drilling, if you want to really make this thing in R3, you have to cut a little hole here to let this other part pass through it. Now this hole doesn't actually exist in the real shape, topologically speaking, because the real shape is just that. It doesn't have a hole in it. You don't have to cut anything. You just say, I'm gluing these together, and I'm gluing those together. But in R3, it looks like that. So to make, I'm just going to say, to make this in R3, we need to allow the shape to pass through itself. But this is not actually part of the true shape in a topological sense. The true shape doesn't have that little thing where it goes through itself. Can you make maybe you think I'm just like bad at drawing this. Maybe there's some other way to draw it where it doesn't pass through itself. It turns out actually, if you want to draw it in a way where it doesn't pass through itself, you need to use R4. So You cannot make this shape in R3 without one of these self-intersections, but I will say it sort of really lives in R4. You can express this as a subset of R4 with no self-intersections, although I'm not going to try to show you what that would look like. But all right, there's a name for this shape. This is called the Klein bottle. Klein is a person's name, and it's usually written as K. The Klein bottle, and it's something like a higher dimensional version of the Mobius strip. It actually, if you, it's harder to visualize, but it has the same kind of property about the heads and tails coin. If you put a little head-shaped coin here, and then you slide it along this part and into the inside and come back around, it will have flipped its head versus tails over. And I brought some props here, some math props. I just got this less than a year ago. It's a little 3D printed Klein bottle keychain, which I keep on my backpack. I will pass this around if anybody would like to see. Check it out. And I also have a Klein bottle hat, which has, you can actually fall, like if you stick my finger in, my finger's now in that part. And then, so I'll pass this around too. You can try it on if you want. Although I did wash my hair today. You don't have to try it on. Those are kind of cute. The Klein bottle is something that, topologists really like the Klein bottle, and it is an important example of another kind of sort of really. I mean, we refer to it as a two-dimensional surface because the surface of it is flat in the same way that like the surface of a sphere is flat. It's a fancier or a more interesting or a different kind of two-dimensional surface, the Klein bottle. All right. Where's my pencil? Here. I was going to say you can do interesting things with the Klein bottle, which are not like as a shape. When you look at the keychain of it, it looks really weird. But actually, when you're working with it in practice, it's not all that weird. It just involves somewhat of a twist. So we can play, for example, just like you did on the homework, we could play tic-tac-toe on the Klein bottle. Toe with an E on it, I guess so, on the Klein bottle. So in that case, you did this with the torus on the homework last week, but you might as well do it on the Klein bottle. It's not really any different, although it is a little weird. So on the Klein bottle, your job on the homework for the torus was to say, like, what are some winning moves on the torus that are not traditional winning moves on a flat tic-tac-toe board. On the Klein bottle, here I was able to find this. This actually is a winning configuration on the tic-tac-toe on the Klein bottle. This is winning because, if I draw this again, I can, starting here, I can go diagonally like that. And now, where does this diagonal line go once I leave the shape up top? It ends up, so this point right here is actually glued with that point on the bottom because of the twisting on the vertical side. And then this diagonal line, again, because of the twisting, actually, it leaves this point going that way. And so that's a 3 in a row on the Klein bottle. Whereas on the torus, that's not 3 in a row, but on the Klein bottle it is. All right. Fun times. You might worry that isn't like maybe everything is winning on a Klein bottle just because of the weird twisting, but it's not so actually. Here's a configuration. This is weird because traditional tic-tac-toe is completely symmetric. This here is just a rotation of that, but actually this is not winning on the Klein bottle because there's a difference on the Klein bottle. There is an asymmetry because the top and the bottom are twisted, but the left and the right side are not twisted. And so actually there is a difference between these two guys going across the top versus these two guys going across the side. This actually is not winning. Although it's a little hard to tell, but you have to think through what are all the different possible ways I could try to draw the arrow, and it just turns out that none of them work. For example, you might try, what about this? Go here to here. Well, because of the way the Klein bottle works, the two vertical sides are glued without a twist, and so that red line would just continue down here, and then they're not 3 in a row. Whereas on the Klein bottle, it would have gone up the other way. All right. All right, we got 10 minutes. I got one more weird shape for you. You can tell all your friends about these wild and weird shapes. One more. Remember, the torus is this, no twists, right? That's the torus. The Klein bottle is where you twist. I drew it twisting the top gluing. This is the Klein bottle. Anybody want to get a little crazier? What if you twist in both directions? Again, this is something that you can do. You could easily make a Pac-Man that acts that way. So this would be twisting in both directions. So I'm going to go like that. All right. This is yet another weird shape. This is called the projective plane. And unfortunately, it's not even really possible to draw a diagram of this in R3, the way that you can think of the Klein bottle as like that shape, the hat, which has one place where it has to go through itself. The projected plane, actually, you can't even draw like that. It's so mixed up that there's no good way to draw it at all in the plane. One way that you could think about this is I could draw part of the identifications, like if I just glue the two vertical sides together, temporarily ignoring the top and the bottom. Actually, what that is the Mobius strip, right? Because it's just the two sides, but you twist them. So that looks like, here's my drawing of the Mobius strip. All right. So this is when I glued the two sides together like that. You have to twist one of them. What the projected plane is, it's you take that and then, you know, the Mobius strip has sort of that and that. That's where the two, the top and the bottom will end up. Sorry, they should be twisted. And now you glue the top edge to the bottom edge here. That's how you get the projective plane. It involves, like, if you were trying to do this in R3, it's not going to work. It involves very, you have to sort of do self-intersections infinitely many times, which doesn't lead to a good picture. All right. Another way of thinking about this is the same as my first drawing here had the arrows like this. If you notice, what we have here is sort of, well, this arrow and then goes against that one. This is actually the same shape as if you started with a circle divided into two parts and you glued the two sides of the circle but with a twist. This, again, is not possible to do in R3, but these are actually equivalent. And so one way to think about this is like this shape. If you are like a little Pac-Man in here, what it means is every time you go off the edge of the circle, you come back on the opposite side. All right, and that's not so weird, is it? I mean, it's kind of like the real Pac-Man comes, but on a rectangle, it comes back on the opposite side. If you do the same thing on a circle, though, this is the projective plane. Not so strange, but if you try to think of it in R3, it's very strange indeed. All right. Just a few more moments can I say about the projective plane. This is called, so the fancy word for this, or the notation that's usually used is RP2. This is the projective plane. There is such a thing as RP3. That would be if you start with a three-dimensional cube and then glue all opposite sides together with a twist. That's the RP3. Or you could think of it as a sphere in which you glue the top hemisphere to the bottom hemisphere, but flipped over. Strange. Anyway, we could do tic-tac-toe on here also. So what would a winning board on the projective plane, they can look very weird indeed. I came up with a few examples. I'm sure any of you could come up with these. So this is a winning configuration on the RP2 because you go out here and it comes back on the bottom like that, because the right side has been glued to the left side but with a twist. It's a little more interesting when you when you consider diagonals. So actually this is a winning configuration on RP2 because I can go, actually you might think, can I go like here and then come over there? Actually that is not correct, because when you wrap around it should go down to this point, not up there. So it's not that way. But if you start here and go diagonally this way, this point down here, this point here is the same as this point, but twisted, so that red line will continue going there. And then that point on the left is the same as the point on the right down here, but it's twisted so the line continues up. So it now goes here and goes up. So that is that's a winning, starting here, this is a winning move. Continuing there, which goes up there. And I wrecked my picture by trying to make it better. All right, so these are both winning configurations in tic-tac-toe on the projective plane. All right, I think that's about all I wanted to say. So I just wanted to show you some important examples of other kinds of topological spaces that you can make with these kind of quotients. For next time, we will start talking something completely different. Actually, we're going to start the next chapter, which is about functions. We haven't talked about functions at all the whole semester, so we got to talk about functions. We'll do that next time. All right, see you then.